In this video I want to look at the basic trig identities, two of which you will have come across before, but I think it's worth just recapping them and seeing the proof of them again. And then I want to develop a couple more as well. You need to make sure that you are familiar with the reciprocal trig functions in order to be able to understand the last couple of identities that I'm going to look at here. So the first couple of identities. So imagine, if you will, please, a point P with coordinates x and y on an xy standard xy set of axes on a grid. So my axes, which I ought to do really. So here's x-axis, here's the y-axis. Here's my point P floating around somewhere, and I've constructed a right-angled triangle from the origin to P as the hypotenuse, and then lines parallel to the two axes completing the right-angled triangle. So we've got a right angle down at the bottom right-hand corner as you're looking at it there. So with that information there, then we can see that the base of this triangle is going to have length x, whatever the x coordinate of the point P is, and the height of the right angled triangle there is going to have, the right angled triangle is going to have a height of y, whatever the y coordinate of the point P is. And just for the sake of argument, we'll talk about the hypotenuse, the distance from the origin of the point P, and we usually give that the label r. We use r there for a variety of reasons, but largely because that's going to be fixed if we allow P to rotate around the origin in a circular fashion. So it's going to be the radius of the circle that it would make, but we're just going to think about the fixed point P there. Just thinking about the basic definitions of our three fundamental trig functions, with an angle made by the radius and the hypotenuse, therefore if it makes an angle of theta with the, sorry about that, little more looks like a bauble, an angle theta between the positive x-axis and the hypotenuse of my right angled triangle. If we call that angle theta there, then we can talk about sine theta in terms of the coordinates or the lengths on the triangle. Sine theta there, opposite over hypotenuse, just going to be y over r, and cos theta as the adjacent over hypotenuse is going to be x over r, and of course then tan theta is just going to be y over x. And you will be familiar with the first two identities that we're going to look at, but here's where they come from again. So tan theta as y over x, we can think of that as being the same as, oops, sorry, equal sign. We can think of y over x as being the same as y over r times r over x. And y over r is sine theta, and r over x is the reciprocal of cos theta, so that's 1 over cos theta. Of course, now that we know about our reciprocal functions, we could have that as, which one would it be? It would be sec theta there, wouldn't it? But actually I'm going to think about it just as being sine theta over cos theta. And there's our first fundamental trig identity, tan theta being equal to sine theta over cos theta. Oops. So that's our first identity. The second identity, known as the Pythagorean identity, comes from us thinking clearly about Pythagoras with this right-angled triangle. So we can look at that as just Pythagoras. Oops. Can't spell Pythagoras. Based on this right-angled triangle here, we know that x squared plus y squared equals r squared. And then if we divide throughout that by r squared, that's going to give us something equivalent to x over r all squared plus y over r all squared equals 1. And x over r is just cos theta and y over r is just sine theta. So this is equivalent to us saying cos squared theta plus sine squared theta equals 1, or often quoted the other way around, sine squared theta plus cos squared theta equals 1, but it doesn't matter which way around we have those, of course. So those are our two fundamental trigonometric identities: tan theta equals sine theta over cos theta, and cos squared theta plus sine squared theta equals 1. And I think that you should be familiar with those two. So what I want to do now that we've seen about reciprocal trig functions as well, we can now develop these by combining them in various different ways. We can develop these to establish a couple more. Just a little reminder before I do that of the reciprocal functions. So we had sec theta. I'll just do this in pencil here because it's not really part of it, it's just a reminder. Sec theta, if you recall, was 1 over cos theta, and cosec theta is the same as 1 over sine theta, and the last of those was cot theta, which is the same as 1 over tan theta. So if we start from our Pythagorean identity about cos squared plus sine squared equals 1, one that you can see still on the screen there, just at the top of the screen now. If we start from our Pythagorean identity there, cos squared theta plus sine squared theta equals 1. And then we can divide. Let's start out by dividing through by sine squared theta. Then that's going to give us cos squared theta over sine squared theta plus 1 equals 1 over sine squared theta. Cos squared theta over sine squared theta is the same as cos theta over sine theta all squared. And 1 over sine squared theta is the same as 1 over sine theta all squared, or just the bottom squared if you prefer, don't mind which one you go for there. And 1 over sine theta is, of course, cosec theta, so we can have this right-hand side of this as cosec squared theta. Cos theta over sine theta is, if we just flip back up to this one, it's the reciprocal of sine theta over cos theta. So that's 1 over tan theta. So we can have this bit here as 1 over tan theta all squared, but 1 over tan theta, remember, is cot theta. So we can replace this cos theta over sine theta all squared with cot squared theta. And we've got our plus 1, and then our 1 over sine squared theta there is cosec squared theta. So there's a third identity for us involving a couple of the reciprocal trig functions, but still kind of Pythagorean in its format. So there's a third identity that we have now. And then we chose there to divide by sine squared theta, but if we go back to our basic Pythagorean identity, cos squared theta plus sine squared theta equals 1. And this time, if we decide to divide through by cos squared theta, clearly cos squared theta there is going to turn into 1. Here we're going to have sine squared theta over cos squared theta. And on the right hand side there we'll have 1 over cos squared theta. And by a similar argument from the one that we had above, sine squared theta over cos squared theta is the same as the square of sine theta over cos theta. Sine theta over cos theta gives me tan theta, so here I've got really 1 plus the square of tan theta, or 1 plus tan squared theta. And 1 over cos squared theta is the same as the square of 1 over cos theta, but 1 over cos theta is sec theta. So here we have 1 plus tan squared theta equals sec squared theta, which gives us another identity that proves to be quite useful. And involving another of the reciprocal trig functions. So we've got all three reciprocal trig functions in some form of identity now, and altogether we have these four. We have tan theta equals sine theta over cos theta, cos squared theta plus sine squared theta equals 1, so those original two, which I think you're probably familiar with already. And now we've developed a couple more. Cot squared theta plus 1 equals cosec squared theta, and 1 plus tan squared theta equals sec squared theta.